Today we're going to talk about shape memory alloy manufacturing. Shape memory alloys, also known as SMAs, are a unique category of metals with amazing capabilities. They display behaviors that are not possible with other metals and is described by shape memory effect. They have an ability to deform by large amounts compared to other metals and recover their original shape. Today's presenters will be myself, Adam Ramsey from St. Paul, Minnesota, Samantha Hodges from San Diego, California, Sean Kavanaugh from Ottumwa, Iowa, Jesse Ortel from Okoboji, Iowa, and Jeff Randall from Hugo, Minnesota. We will be covering what are SMAs, the history and trends of SMAs, application advantages of SMAs, disadvantages of SMAs, materials that SMAs are made out of, concepts of SMAs, manufacturing raw stock, shape setting, post-secondary machining operations, new technologies, and conclusion.
What are shape memory alloys? Shape memory alloys, or SMAs, are considered by many as one of the most promising smart materials. SMAs are peculiar materials with the ability to recover from apparent permanent deformation of 10% or more and still exhibit desirable characteristics of other metals like resistance, stiffness, and workability. On this next page is the phase transformation process for shape memory alloys. So you can see it starts with its original shape. At room temperature or low temperature is bent, deformed, heated, and it reverts back to its original shape. All right, so shape memory alloys, the most common shape memory alloy is a combination roughly of 50% nickel and 50% titanium. There are two crystal structures that allow them to have this memory behavior, and it is austenite and martensite. There are two shape memory effects for shape memory alloys. It is the one-way shape memory alloy, or one-way shape memory effect, and the two-way shape memory effect. So here is a table of the different shape memory alloys who have the shape memory effect. One-way shape memory alloys exhibit shape memory only upon heating. So here is, in the bottom corner, is an image of the martensite room temperature, one-way shape alloy, shape memory alloy, and then deformed, and then it reverts back, is heated and reverts back to its original shape. Two-way shape memory is materials that exhibit shape memory upon heating and also undergo change upon recooling. So it's unique in that it is spontaneous with temperature changing without the need of external forces. So again, here's an image of it. Martensite room temperature, irreversible deformation at room temperature or cool temperature, is heated at austenite temperature and then cooling to martensite. The history of shape memory alloys, it was originally discovered in the 1930s by a Swedish chemist, Arne Olander, who discovered the gold cadmium alloy. Unfortunately, nothing was done with it at that point in time, and it wasn't until the 1950s, 1960s, when the Navy discovered the first nickel titanium alloy, rediscovering them, that they first got their big break and started becoming more widely used in a variety of products. So research, as you can see, from the 1960s, around 1962, about 2009 in this table, the research increased significantly. And since 2009, there have been about 109,000 publications. Future trends of shape memory alloys, they are being increasingly seen in the medical and biomedical field, being used for blood clot removal, plaque buildup, engineered limbs, bracing structures, aiding with internal fixation of bone fracture, just to name a few. Also, NASA has created a shape memory alloy actuator to be able to fold the wings of an F-18 Hornet's wings 0 to 90 degrees up or down while in flight. And I actually have a video of that right here.
Spanwise adaptive wing is about moving wing sections in flight to improve aircraft efficiency, whether it's drag reduction or control authority or better stability. We are not the first ones that's doing this. In fact, this dates back to the early 60s, like the example of the XB-70. But what's different here and what's new is how do we fold those wings? At the heart of Benoit's adaptive wing project, we have this new multifunctional materials known as shape memory alloys, which change shape or remember different shapes as you heat them and cool them and can be used as actuators. Recently, a few months back, we did a flight test on a subscale aircraft using this new actuators. And in fact, for the first time, we use a new high-temperature shape memory alloys developed at NASA Glenn based on nickel, titanium, hafnium, and these new materials have the right characteristics for flight. So now that we've done this flight test, we wanted to transition to a full-scale test, being this F-18 wing sections that we're demonstrating on. And with that, we took the existing hardware of the folding mechanism, which is a motor and electric motor, and
Hey guys, Sean Cavanaugh with ME428 and the group on shape memory alloys. I'm going to get started on my aspect of the discussion by talking about the applications and advantages of shape memory alloys. So there's an ever-increasing number of applications for these things. They originally were seen in aviation. The first commercial use was in 1969 on the F-14 Tomcat. And basically it was used as a shrink-to-fit coupling, and you can kind of see an example of this in the SMA coupler diagram that's here. But basically they're less weight and they have less cost, and they're a pretty unique application for a lot of different things. They can replace electric motors, they can replace pneumatic and hydraulic actuators. They have a variety of applications. So GM specifically, in 2012, they put out an article talking about smart materials and their use for like weight reduction. In the Corvette, for example, they were talking about replacing actuators, again pneumatic and hydraulic actuators, and certain electric motors with these shape memory alloys. For aviation, one of the main advantages is the actual reduction in weight, because any weight reduction on structure or components kind of results in a payload increase given the same aircraft, and a payload increase means more bags or more passengers, etc. So if there's a wide array of different applications on an aircraft for shape memory alloys to replace things like actuators or motors, you have a potentially lighter airframe that you're able to obviously just put more passengers or payload on, and that's more revenue for the company, for the airline. It's an advantage. In robotics industry, you see their uses, micro actuators and artificial muscles. I'm sure some of you have seen some of the artificial muscles and things like that on some of these Japanese robots that are doing some pretty cool things now. Biomedical industry uses them for braces and dentistry, as well as tendon-to-bone anchors and glasses frames. I'm pretty sure we've all seen the glasses frames. These aren't them, so I'm not going to break these. But some of them you can like bend them and twist them, and they just like return back to their original form. It's a pretty impressive use of shape memory alloys. They are able to respond to external stimuli as well, like heat and cold. So there are some disadvantages. Despite wide-ranging applications, the number of viable products hasn't really lived up to the potential existing in their available applications. And a big part of the reason for this is just research and development as far as like engineering and scientific understanding of the properties of these materials. There's not a wide base of understanding yet. People are still working on understanding them, but it acts as somewhat of a disadvantage for industry when they're reluctant to invest money in something they're not 100% knowledgeable about. So there's several alloys for SMA. There's like iron, manganese, silicone, copper, zinc, aluminum, and copper, aluminum, nickel. And all of these alloys have commercial uses, but they have disadvantages like brittleness, instability, and poor thermomechanical performance. So by far, the one that's used the most is a nickel-based alloy that's NiTi. It's nickel titanium, and it has a lot better performance in a lot of ways than other SMAs. Certain SMAs kind of have a unique niche where they fit the best, but the nickel titanium alloy has the most broad range of uses, and it's by far the most common alloy. So we're going to talk a little bit about what causes the shape memory effect and about superelasticity as we go through here. But SMAs have structural variety. They exist in 2 different phases and are further comprised of 3 different crystal structures. So we've got an austenitic and a martensitic phase, and then there's a D-twinned and a twinned martensitic phase, and there's just the austenitic phase. And so what happens is austenitic structures are stable at high temperatures. So when the material is at a high temperature, it exists in this austenitic phase. And as it cools down, it transitions into a martensitic phase because the martensitic structures are stable at lower temperatures. So heating in SMA results in a change from the martensitic structure to the austenitic structure. And the phase change from martensitic to austenitic begins at the austenitic start temp and ends at the austenitic finish temp. Cooling is like vice versa. Cooling in SMA, it goes from austenitic to martensitic. And so the phase change begins at the martensitic start temp and ends at the martensitic finish temp. And you can kind of see this nickel titanium SMA phase transformation chart here. That's just a temperature versus strain graph. And you can kind of see the hysteresis of it and how it works regarding the heating and then the recooling, and the martensitic to austenitic transitions are kind of listed on the left. You can see austenitic finish and start temps and the martensitic finish and start temps. So the shape memory effect has kind of three different characteristics. There's three different kinds. There's like a one-way shape memory effect where the material stays deformed until heated back to the austenitic phase, at which time it returns to its original shape. There's the two-way memory effect, which is where the material can remember a shape at both temperature ranges. So heating or cooling forces it to take on that particular temperature shape based on the martensitic or austenitic phase. So superelasticity, which is kind of the third one, is where the material can have stress applied, and if the temperature is in a certain range, it will return to the original shape with no thermal activation at all. So the heating and the cooling isn't a necessary part of the superelasticity. It will return to its original shape without thermal activation. So that's it for my aspect of the presentation. Thanks.
Have you ever seen a material do this when it gets heated? This is not an ordinary material. This is a shape memory material. It has the ability to remember a specific shape and change into that shape when heated. So how do these materials work? It is all based on phase transformations. You've probably seen phase transformations when water freezes. This is a transformation from liquid water to solid water. There is also a phase change when water boils. Here, the liquid water becomes water vapor. But what is the difference between the phases? The difference is how the individual water molecules are arranged. In liquid water, they are loosely packed together so they can move past one another. In ice, they are tightly packed together and they can't change places. But did you know there are actually multiple solid phases of ice? There's a hexagonal ice phase that is stable until -150 degrees Fahrenheit, and a cubic ice phase that is only stable below -150 degrees Fahrenheit. So how does this fit into shape memory materials? These materials also have multiple solid phases. There is a low temperature phase that is called martensite. But if we increase the temperature, the atomic alignment changes into another phase, called austenite. So at low temperatures, we have martensite, and at high temperatures, we have austenite.
Hi there, my name is Jesse Ortel, and I am part of the Shape Memory Alloy Group. Today, I get the pleasure of talking to you about the manufacturing of the raw stock for these shape memory alloys. So, with these shape memory alloys, or SMAs as I'll refer to them through the rest of the video, the basic controlling mechanism here is the chemical composition. The chemical composition plays a crucial role in the development of these shape memory alloys and achieving the properties that are so desirable, the property of them returning to their shape after being reheated that we do not find in most other alloys. So where does this begin? It begins in the melting process. So when we're making these alloys, we're faced with two primary impurities that are common. So the first one being a carbide and the second one being an oxide. So since the majority of these shape memory alloys are made with titanium, we see a lot of the TIC impurities. These impurities are detrimental to the fatigue properties, and there's been a direct correlation found between the fatigue breaking point and the level of these TIC impurities. So we want to eliminate those as much as possible. And as I said earlier, we also have oxides that we have to try to account for. And this again begins in the melting process. So there are two primary melting processes for these SMAs. The first one being in vacuum induction melting, or VIM, and the other one is vacuum arc remelting, or VAR. Okay, so vacuum induction melting. In this process, raw nickel pellets as well as titanium bars are placed in a graphite crucible and then melted. So why use a graphite crucible? Well, the graphite can withstand the amount of heat required to melt that titanium. Titanium requires extremely high heat to turn into molten material. And in order for the mixture to happen correctly, we need to achieve that heat. So that is why we use graphite. But with graphite, we're faced with the challenge of carbon infusion into the material. So how do we combat that? Well, we place the titanium bars on top of the nickel pellets. Carbon diffuses into nickel a lot easier than it does titanium. So we put those titanium bars on top to create this film. It's a TIC film that sort of acts like a barrier, preventing more carbon from entering the material than we want. And it has been found that the more you use the crucible, this graphite crucible, the better the TIC film is, and we get a more pure substance, more pure final product in the end. Okay, so the next one we have is the vacuum arc remelting. In this one, the starting elements, typically titanium and nickel, are placed into either a consumable or non-consumable electrode crucible. Then they are melted together. So this here, we're eliminating the carbon infusion, and we're eliminating all other issues that were faced in the vacuum induction melting. But this vacuum arc remelting does require multiple times, going through it multiple times. But we do see more pure and higher quality alloys. The only downside is the fact that you have to do this multiple times. So it has been found that the best process to make these shape memory alloys is combining the two. First, you do a vacuum induction melting, and then you follow that up with a vacuum arc remelting. And this leads to about as pure as we can possibly achieve. So once we have our ingot, in a sense, so we've melted it, we have it together. Next thing we have to do is hot work it. So we hot work it using a forging technique of some sort, either extrusion, forging, stuff like that. And this is done at the 800 to 950 degrees Celsius range. And what it does, it achieves the homogenization of the microstructure and reduces the solidification grain texture adjustment. So we hot work it, we get it ready to go, and next we move into the cold working process. So at this point, our ingot or alloy is in an intermediate form, and we put it through a series of cold working processes. But while we're cold working it, we have to do periodic annealing treatments to set up the microstructural properties that were obtained during the cold working. So we have to do some heat treatment periodically in the middle of this cold working process, typically done in that 400 to 600 degrees Celsius range. So not all the way up to the hot working level, but we do anneal it and then quick quench it and then keep doing our cold working. But it has been found that the maximum cold working that we can do with these shape memory alloys is about 40%. After that, we start affecting the properties and we don't end up with that shape memory effect. So the typical, most common form of the cold working that is done with these is drawing. So what we do here, the rods of the alloy are drawn through dies to form smaller diameter wire. Pretty common in most other alloy working techniques. It's not shape memory specific, but that's typically how it is done. The next thing we see is rolling. Again, another very common cold working technique. Here the alloy starts out as a plate and then it is run through a series of rollers. That force that is applied by the roller changes the plate into a thinner sheet. These thin sheets are super desirable though for manufacturers because they provide design flexibility. It allows us to create things. It's much easier to work with a flat sheet of metal and change it to something than trying to design that shape right off the bat. And then finally, we have tube forming. So Tube forming is kind of the way of the future, per se, with these shape memory alloys. Here, a bar of the alloy is gun drilled, and this creates a hollow. And then the tube hollow is subjected to cross-sectional area reduction. We do this by successfully smaller dies to form the outer diameter, and then successfully smaller mandrels to form that inner diameter during the drawing process. So once we have this tube formed, the most common medical use for this right now is stents to open up arteries and stuff like that to allow for better blood flow. These are super important, and this is kind of where they're headed with these shape memory alloys currently. So tube forming is super important. With that being said, that is pretty much the basics of the manufacturing of the raw stock here. So I'm going to leave it up to my colleagues to finish up and give you some more insight into the applications and further heat treatments with these shape memory alloys. Thank you. Bye.
How do we set the memory shape? To set the shape that we want, we must hold the material in the austenite phase at high temperatures. Here, we have used screws to hold the wire in place on a metal plate, which we then put into the furnace to heat it. Inside the furnace, the wire transforms into austenite, which sets the memory shape. When we cool it down, it transforms into martensite, but it does so without changing the shape. In the graphic, you can see that the atoms have the martensite structure, but they align in a zigzag pattern so that the overall shape does not change. Now we can bend the wire however we like. The material does not change phase, but the alignment pattern changes slightly so that they align in one direction. This results in a permanent shape change. Now if we heat up the wire, it goes through the phase change from martensite to austenite and it returns back to its original shape. We can repeat this for almost any shape we want. Shape memory materials also exhibit another special property called superelasticity. Here's the same shape we saw before, and now we will pull it. But unlike before, this time the shape doesn't change, but it goes right back to its original shape. This is called superelasticity. This also works because of phase transformations. This material is a slightly different composition, so that at room temperature it is in the austenite phase. If we stress the material, we can force it into the martensite phase, and this will change the shape. But if we release the stress, it goes right back to the austenite phase and the original shape because that is where it is stable at this temperature. You may have seen this before in eyeglasses that can be stretched without being permanently bent. We've shown you how the shape memory effect and superelasticity work based on phase transformations. This is an example of how material scientists study materials. They try to explain observed properties in terms of the internal structure. Then, once they understand the underlying principles, they can use them to make even better materials.
Shape setting is the process used to form the recall state of SMAs. The process involves forming the SMA around a fixture and restraining it to its desired shape. Then the fixture in the SMA undergoes a heat treatment to learn this new shape. For very complex designs and tight tolerances, this process may need to be repeated multiple times to help reduce internal stresses in the material. To set the SMA material, the material needs to be heated above 500 degrees Celsius. This will bring the material's grain structure past the austenite phase into the perlite phase. The actual temperature and dwell time will depend upon the alloy that is being used. The fixture is then quenched, usually in water, to prevent further aging and set the desired shape. Aging is the process of heating the SMA like nitinol to precipitate out nickel. This is done to fine-tune the properties of the SMA. Aging is generally done during the shape setting process. When milling, turning, and drilling is done on SMAs after shape setting, Particular care needs to be given on how much heat is being generated. When doing these operations to material like nitinol, it can be difficult. Nitinol is a hard material in its cold work state. It is also extremely abrasive due to its tough titanium oxide layer on its surface. Some guidelines to consider when working with SMAs after shape setting are the CNC controlled speeds and feeds. Using a strong coolant flood and carbide tools are all vital. Expect rapid tool wear. Very small features such as holes less than 1 millimeter in diameter should be avoided. Turning can be more successful than milling due to its uninterrupted nature of the cut. Tapping is also strongly discouraged. SMAs can also be laser cut. For example, during the manufacture of a cardiovascular stent, the tube is rotated and moved longitudinally under the focused laser beam to create the desired cut geometry. Laser cutting has become one of the most commonly utilized machining technologies for the manufacture of SMA devices, mainly due to the extreme precision and low thermal input characteristics. Current laser technologies allow for cutting the material as thin as 25 microns to a thickness of greater than 0.8 millimeters. The ability of the laser system to cut fine complex geometry largely depends on the motion system and the spot size of the focused laser beam. In laser machining, the kerf width is dependent on the laser spot size. Smaller kerf widths allow for the designs with smaller and more complex geometry, and therefore generally considered to be better. Ultra-short femtosecond lasers have the highest beam quality and can achieve kerf widths as low as 5 microns when cutting relatively thin, less than 50 micron components. SMAs can also be wire EDM'd. A spark discharges from the wire and ablates the material closest to the wire. There is no contact between the wire and the workpiece during the cutting. The recast heat affected zone thickness is minimized by the cutting workpiece while submerged in deionized water. Laser, plasma, and resistance welding processes are all commonly used for joining SMA components. The challenge for welded SMA components is the large amount of heat input required to create the joint. The weld itself, as well as the heat affected zone adjacent to the joint, will have different mechanical and functional properties. In laser, plasma, and resistance welding, the fusion zone will have an as-cast structure. CNC pulse laser systems are the most common welding processes used for assembling SMA components. The high-speed, non-contact, low-heat input characteristics of this process make it very attractive in the manufacture of nitinol medical devices. Spot laser processes are commonly used for tack weld type applications. For example, welding of a collar or a tube to the end of a wire component. Seam welds are also commonly applied where overlapping of pulses is achieved through timing stage motion with the pulsing frequency of the laser source. An overlapping of greater than 80% is usually recommended for hermetic sealing type applications. Crimping is a very robust method for joining SMAs to itself or dissimilar materials. The major drawbacks include rather bulky profile of the crimp and the process challenges associated with multi-piece construction. Crimping is typically the joining method of choice when considering the termination of wire ends in wire form devices. Important design considerations include the crimp must be ductile enough to be plastically deformed around the components to be joined. Using a dissimilar material such as stainless steel for the crimp tube can lead to issues associated with incompatibility of material properties and galvanic corrosion. SMAs can also undergo blasting. Grit blasting and microblasting are methods used to remove oxides, surface marks, and processing material contaminants from upstream processes such as drilling, heat treatment, laser cutting, EDM, or localized heat processes. Grit blasting is usually performed on tubes, wires, and is a relatively large-scale process, whereas microblasting is performed on smaller-scale components. The abrasive action is capable of removing materials such as the recast layer, heat-affected zones, microcracks found around the nitinol surface, and can remove significant amounts of material. Mechanical tubuling is an operation where the components are loaded into a vessel containing abrasive media, and the vessel is agitated via rotary or vibrational means. The action of the media on the parts serves to smooth the surface and round sharp edges. Tumbling is typically not effective in removing large amounts of material. It is more effective at breaking edges and rounding sharp features. SMAs can also undergo chemical processing such as etching. Etching is also known as pickling. It is common practice for oxide removal and removing a relatively large volume of material from the SMA surface. An etch part will have a light, bright surface finish. Common examples of chemical etching process include the removal of the brittle recast layer from laser cut components, removal of any transfer material from the wire electrode of EDM cut components. Electropolishing is an electrochemical process that removes material from the surface of the SMA component. During electropolishing, electrical current flows over the peaks present on the relatively rough surface and creates high current density at these locations. This results in the preferential removal of high spots during electrical polishing, which makes it ideal for eliminating burrs and ultimately lowering and improving surface roughness. A properly electrical polished part will have a lustrous mirror-like surface that will appear as such even at higher magnifications. Passivation is the modification of the surface chemistry to make the SMA device less reactive or more resistant when exposed to certain environmental factors. SMAs, like nitinol, have naturally occurring passive titanium oxide layer that forms on surface. As a result, different passivation techniques have been developed for nitinol medical devices, such as chemical passivation or even boiling in water. Laser marking of SMA components is common practice. Examples of laser marking applications include visual indicators such as depth marks or labels, manufacturing lot numbers, or even QR codes and company logos. There are two different modes of laser marking, which include ablation and annealing. During ablation type laser marking process, the metallic, often shiny appearance is created through melting and ablating the surface material. Annealing type process, on the other hand, does not cause any changes in the macroscopic surface topography, but instead changes the color of the SMA surface through modification of the oxide layer. Coating and plating SMAs can be coated with materials such as PTFE, FEP, Parylene, diamond light coating, etc. to improve lubricity or wear resistance.
Hi, I'm Jeff Randall, and I'm going to talk about new technologies in manufacturing of shape memory alloys. So there has been some non-conventional and innovative working processes that have been investigated and studied lately. And in the area of creating a material that's ready to use from the melt creation, they've been looking at a process to do near net shaped components, porous components, thin film material, and even foams that are made out of shape memory alloys. In these processes, there is a melt spinning, a powder metallurgy and additive manufacturing, photolithographic for thin films, and liquid infiltration for foams. In the melt spinning process, the goal is to eliminate longer manufacturing processes that were discussed earlier and create a ribbon or strip right from the raw material. This process is accomplished by a rapid solidification from the melted alloy. Here's a picture of that process and what is going on. The melted alloy will fall onto a rotating wheel, and as it has that rapid solidification and starts to solidify, it is pulled and it creates this ribbon or strip. The principal characteristics in melt spinning it has proven that there is lower average grain sizes. You can introduce a region of amorphous material in some cases, and they're finding that you can introduce some textures due to the rapid cooling process. The results so far have been inferior for mechanical and shape memory properties when you're comparing it to the normal bulk processes, but they have found that adding a rolling or thermal treatment can improve the material performances and give better size and microscopic feature control. Powder metallurgy. The main reason here is to create near net shape components and porous components. The processes looked at for shape memory alloys has been the MIM, the SHS, and even sintering under pressure. Outside of the typical characteristics that powder metallurgy has, they have found porosity ranges from 40 to 70%, with small pore sizes ranging from 60 to 500 microns. The processing issues with powder metallurgy has been oxygen content, controlling of the chemical final composition. You get formation of secondary phases, the microstructural homogeneity of the final material, and they found that there is some limited mechanical response, which has been really caused by induced cracks in the porous regions. The main application of interest has been in biomedical, and they have the potential to use these as implanted material to promote osteosynthesis. And the orthopedic industry has implemented powder metallurgy for creating a nitinol, which has a porous implant for spinal fusion, which is done by the SHS process. So for additive manufacturing, it is 3D printing, and the reasons you would want to do shape memory alloys in 3D printing is to create a near net shape component. You get quick production process. You get a final product that has, you get reduced final product costs, and you can obtain samples much quicker than any other process. The 3D printing processes used have been selective laser melting, electron beam melting, fused disposition melting, wire arc additive manufacturing, and even laser engineered net shaping. Now, majority of the stuff has been done in selective laser melting, the SLM, and that's the one I'll discuss here. Some process parameters that you need to keep in mind when using this for shape memory alloys is the energy density, which is controlled by your laser power, your scanning speed, your layer thickness, and your hatch spacing. And the other area of interest to keep in mind when doing the SMAs is your scanning strategy. Is it unidirectional, is it bidirectional, spiral, or island scanning? The 3D printing process does have issues, and some of them are a dense defect-free product is not guaranteed. You get uncommon microstructures, which are extremely small, which are caused by extremely small melt pools, fast cooling, and the remelting and reheating of the previous layer as you're adding the next layer down. It does take high melting temperatures to do this process, and in order to do the high melting temperatures, you need a source of that energy to create that melting. The materials that have been done on 3D printing have been titanium and titanium alloys, moragonal steels, stainless steels, tantalum, I guess that's a chromium alloys, aluminum alloys, and nitinol. So the results with the SLM process and nitinol have found that there is higher density and crack-free parts, but there is care in the process environment to avoid oxygen and nitrogen pickup to increase the density of the impurities. It is difficult to control transformation temperatures. The nickel does evaporate off in this process because of the high heat, and then usually the mechanical properties have been inferior, along with the functional properties compared to the normal materials, but repetitive laser scanning can assist improving the functionality properties. Some applications where the 3D printing has come in is in medical implants. The fashion industry has created they call it an adrenaline dress, and that was shown on 2015 Fashion Week. There's a company that has made sports bras, and then there was also mention of agricultural design with window shades. The window shades will react to the temperature in the room to open and close to allow the light to come in. Here's a picture of the 3D printed adrenaline dress that will react to the person's adrenaline in the body, which really reacts from the temperature of the body. Here's a picture of a 3D printed SMA. And then this is a picture of the sports bras that have SMA material embedded into the neoprene. And as your body temperature increases, it opens up vents to allow it to cool down. And when your temperature goes down, they close the vents kind of shrink up and close. So one really new area of manufacturing is what they refer to as 4D printing. It's 3D printing plus the fourth dimension, which is time. MIT is looking at this, and there's not a lot of information out there yet, but they did say that layers of stimulus responsive composite or multi-material with varying properties can be accomplished by the 4D printing. You can get parts that can react to stimuli from natural environments or through human interventions, physical or chemical change of state through time. And they know that very new technology with a lot of challenge. This is a very new technology with a lot of challenges, still needing a lot of resolutions. So hopefully we'll find out more about that in the near future. So one area that is creating thin films, which is done by the photolithographic method, and it produces nitinol in these thin films with thicknesses that it can be less than 10 microns. This is done by a sputter deposition, and the nitinol is deposited on a silicon, a glass, or a polymeric substrate, and it's used in miniature pneumatic valves, spacers, and flat panel displays, and devices in microelectromechanical systems. The liquid infiltration method is used, and it's fairly new, and it can create an open cell SMA foam in a leachable bed of silica gel particles. You can obtain uniform microstructures of ligaments and well reproducible open cell morphology. And it's very new, with the research showing mechanical properties that can recover monoaxial compressive strains up to 3%. So in conclusion, we've got shape memory alloys that have been utilized in applications for nearly 50 years. There has been an increase in the research behind the behaviors of the SMAs since then. The SMAs have a variety of material combinations for new areas to apply the SMAs as the understanding of material properties grows. Manufacturing process is the key to obtain final desired properties in the shape memory alloys. Your manufacturing process does establish the three characteristics of the SMAs: the one-way, the two-way, the superlit, and the superelasticity. You need to minimize impurities during the melting process. The hot and cold working is critical to give the SMA the needed shape memory properties. And shape setting does establish the desired shapes after the other manufacturing processes have been done. You do need to remember to take care during your post-processing so you don't damage shape memory properties in any component. And then there are a lot of new technologies that can change the way the manufacturing is done on SMAs. Thank you very much.